Okay, welcome back. I'm Jadi and you're watching Geeking with Jadi. I'm going to speak about GIL in Cpython. It's a very fun to know concept, easy to understand in the beginning. You can go deeper and deeper, and we will check some codes on the Cpython level. It's a C program which runs Python, which compiles to what we know as Python. I wanted to record this video for maybe 1 month, but lazy. And on the other hand, I was thinking, let's wait. Someday I will know exactly everything which is possible to know about it, but it never happens. In the Python world, on the Zen of Python, we say, now is better than never. So let's talk about it. GIL was in the news lots and lots and lots. Python moves to remove the GIL and boost concurrency. Python's GIL, a major obstacle to concurrency, will likely be removed, but slowly. Is it finally time to remove the Python GIL? Goodbye GIL, but will it make Python faster? And lots of other headlines. Here I won't go. Here I will review how programming languages are managing the memory. Then we will see why we need GIL. We will see in general how it is implemented. We will check a few lines of the code in the Cpython. And we will see ideas for removing it and if it helps. We will learn a lot of things, hopefully. But first, let's run a Python interpreter, Python 3. Okay. How programming language manage memory? This is important. But first, let's talk about Python as a language we know vs Cpython. Python is the definition of the programming language we know about. There are some documents called PEP, Python, not improvement, enhancement proposals. If you want to add something to the Python, you write a PEP, you propose a new idea. If it's accepted, it will be part of Python. So Python is a set of documents or ideas or descriptions on how a programming language should work, this specific programming language. Cpython, on the other hand, is the physical word implementation of those ideas in the C language. So Python is just a description of the language. Cpython is a program. When you compile it, it will give you Python exe or any executable you have, ELF executables in Linux or whatever, the one that you can run. And it's the reference implementation of the Python PEPs. This is what Guido is working on and everyone else. This has the GIL, which they are going to remove it after all these years. So when in this video I'm speaking about Python, technically I'm speaking about Cpython implementation of the Python language. When in Cpython I say A equals 60,000, what happens? Cpython goes to the memory, writes 60,000 somewhere in the memory, and says A points to this, creates a reference to this. But say you have a function. You have a function, you call it, something is happening, you create A equals 6. So Python goes to the memory, writes 6, points A to this. Some specific details are here, but just think about it like this. You are continuing, function is finished, this A is not valid anymore. This A is not valid anymore, but 6 is still written in the memory. This is not good because you're wasting memory. What Python does, and every other programming language does, they need to understand this and clear this memory slot. They don't technically clear it, but they know that, okay, next data can go here because nobody is using this. There are different methods to do so. In Python world, it is called reference counting. If A equals 60,000, it writes 60,000, assign A to it, and says, okay, my ref count for this location is 1. If you say B equals A, Python will say, okay, my ref count, because now B equals A, this happens, my ref count to this place is 2. And when the ref count becomes 0, Python knows that I can use this memory slot again, and this can be recycled. Otherwise, if a programming language doesn't understand this will make memory leaks. Your program is running for a long time and consuming more and more and more memory, because there are variables which are not released in different methods. Anyway, this is reference counting method which Cpython uses. There are other methods too. For example, garbage collectors is used by Java. So what we have? We have a memory. This is written there. A is pointing to it by this line. B equals A, so B points to this. Your ref count is 2. Let's check it. Import sys. From sys you can say get ref count for A. It's 3. Why is that? Another point. You are calling a function and sending A to it. So you need to send something to this function. So it creates something, points to this, and calls the function. So my ref count is 3. If I delete B, my ref count will become 1. And if I call the function, it will become 2. You can check this. Del B, ref count is 2. So this is how ref counting works. Very easy, very fast. It's much faster than many other methods. But it has a huge problem. Not huge, but it has a problem. Nowadays we have much better CPUs. Our CPUs do have lots of cores and they can run different instructions at the same time, concurrently at least. What happens in this concurrency? You have 2 different threads and they are running. You have one program and it runs 2 different functions. You have a variable here, A, and its ref count is, for example, 3. You have thread 1, thread 2 running in parallel or concurrently. And you have one Python executable, which we know is Cpython, doing this. These are both into Cpython. What happens if this thread do have something like this? B equals A. So what happens is ask from Cpython, what's the ref count for A? It says ref count is 3. It says, okay, cool. Same thing happens here. Same thread, another thread, you are adding things. It says B equals A. What's the ref count for this one? It says, okay, it's 3, because it's 3. It says, okay, please change it to 4. And this says, please change it to 4. And this will become 4, because 2 times we said, okay, change it to 4. It should have been 5. This is the problem with the concurrency. If you are accessing same data from two different channels, you will see these kind of problems. And you should prevent this. More and more and more CPUs are having more and more and more cores. And your programs need to use this strongness of the CPUs, this power of the CPUs with running different threads. But you are breaking everything, practically everything, and threads are unusable on Cpython unless you have a way to answer to this. The way is called GIL, Global Interpreter Lock. What happens now that we have GIL? You have A equals 5. You have a Python running here, and you have a GIL, Global Interpreter lock. You want to lock the interpreter for yourself. It's like a token. You have two threads and they are running. This wants to say B equals A. It says, okay, I want to do something in Python. Give me the GIL. The token will go here, and this one will have the global interpreter lock. Locks the interpreter for itself and says, okay, what's the reference to the A? It says, okay, now it's 5. It says, okay, change it to 6. A's reference will be 6. This same thread is trying to work. I mean the same code. It can be a different code. It's trying to do the same thing. But because the lock is with this thread 1, the other thread cannot call it. When this thread continued and somewhere didn't need it to run any other Cpython bytecode, it will give back the GIL. GIL is free. This one will acquire the GIL, will ask what's the reference. It says 6, says okay, please change it to 7, and works fine. GIL is global interpreter lock. Only one thread at the moment can run Cpython bytecodes. You know, when you write your programs in Python, they will be converted to bytecodes, and Cpython is running these bytecodes. With GIL, you have a global interpreter lock. Only one thread at a time can ask Python to run bytecodes. So no one can overwrite your programs or your variables or anything. First guess is okay, this is bad, because if this is the case, my programs will run like this, and my multi-threading won't be useful because they have to stop for each other. But remember, GIL is only locks the thread for the Cpython bytecodes when you have to do something with the CPU, a calculation or something. In most cases, our threads are waiting for I/O. You are sending something to the network and waiting some time for it to go back. In this case, you don't need the GIL. So you give back the GIL, wait for the network. This one is doing its calculations here. When calculations is done, it wants to wait for the GUI for a mouse click. So it says, I will wait for I/O. I don't need the GIL. The other one can have the GIL while I'm waiting for I/O. Your programs waits lots and lots of time for things other than CPU or running bytecodes. That's why multi-threading works. But yes, if you have two different threads, both wants to work with CPU, GIL is not a good option, but GIL is our option. In this case, there should first be some implementations. For example, no thread should be able to keep GIL for a super long time. There is a configuration for this. You can say sys get switch interval ID. Yes. Get switch interval. It says no thread can keep the GIL for itself more than this. Sometimes there is another configuration, I believe. For example, it says no more than 100 instructions can be run by any thread before giving back the GIL. So if you ran 100 instructions or this time passed, GIL will go to the next one looking for it. Still not a very great idea. Especially there are cases where, for example, you have super I/O bound thread and super CPU bound thread. This has the GIL, uses it. When it needs to give it back, this is still working with I/O. So gets back the GIL for itself. So you have very small intervals to ask for a GIL. And this one will have the more power over CPU and will starve this one. These are all tested cases. I have a fun case for you here. I have a small program here. Practically, I'm just adding an answer. In the beginning, it's 1, and I'm adding 2 to it. So the first run, if I run add with 1 here, I will get back 3. My add functions uses this variable, the global variable. Then it says for I in range of this number, which is passed here, do this many times, add 2. Very, very CPU incentive, although it's very silly. So I can say Python 3 temp, what was the call of this count? Takes a lot of time. I can say time, it will show me how long it will take. It takes around 3 seconds for the user and this much to the system. 99% of the time is about CPU. So, good example. If I write the exact same thing using threads, so do is the same, start with answer 1, the function is exactly the same, for this many times add 2. What is different is here I have imported threads and I will create 2 threads and I will say each of them should call the add with half of the times I'm going to run it. So in this one I was just calling it once. Here I'm calling it twice but with half the load. If it was a real multi-threading work, the time should be half of this because 2 different threads are adding 2 at the same time. It's a concurrent. I will start my thread and will wait for the thread to finish and will print the answer back. What I will have here, time Python 3 temp count threads. You can see it took a long time. Not much improvement because this is 99% CPU bound. And we talked about the GIL. We start 2 threads. Yes, 2 threads. Each of them wants to run Python code with CPU. So each of them will get the GIL and the other one is just waiting because it doesn't have the GIL. As soon as this is finished, the other one will get the GIL. Finished, I mean this much time passed or 100, whatever your configuration is. So when this is done, this one will get the GIL, this one will get the GIL. Practically, they are not running in parallel. They're just waiting for each other, which is silly. That's why multi-threading programs are not super cool in Python, Cpython, especially if you are using CPU-bound programs. If it's I/O-bound, it's okay. Someone is working with I/O, the other one is doing the calculations. But if both of you want to work on the CPU, it would be a disaster. That's why people have these issues with the GIL. I have the Cpython code on my computer, cdw, cd Cpython. Here you can search for the presence of the GIL and you will see it a lot and it's difficult to remove it. One reason that we have this much GIL on some part was the reason that you are using Python. GIL used to and still lets C integration. We had lots and lots and lots of C libraries and still has, which was being used in Python. Python was able to include C and vice versa. And what happens here, to keep the threading safe, not to write over each other's things, GIL was a huge help. If you were in a Python program and you called C, C were able to tell the Python if it's executing Python or not. It could acquire GIL and release it. That's why Python became this much popular. It was a very small language with limited capabilities, but it was able to work with C libraries because of the GIL. You were able to say, okay, don't write anything, don't execute any Python program anymore till this C program is running. As soon as C was finished, it could say, okay, give back the GIL, and now Python Python were able to run. So this GIL helps a lot in the integration. But nowadays it's slow. If you search in the Cpython, you will see the same thing. If I just do a simple search for GIL, you will see lots and lots and lots of references. In different modules, you have these GILs and other stuff. For example, on the Cpython callbacks, you have this py GIL state release. Releases the GIL in a C program. Oh, there is another one on ensure. Here you ensure that you can have this. Let me go to the reference of this one. If we have it, I'm not sure if I have the tag. No, I don't have the tag. We can check for the, because I don't write C programs. We can check for something like begin allow threads. You have this in many different places in your multiprocessor. For example, here you have a calculation in your C for SHA blah blah. Very CPU bound things. So here you call a macro. You say py begin allow threads. I'm sure I'm just doing my calculations. And here it is finished. You have two different macros for allowing other threads and ending allow other threads. If you want to check what are these, again, if I have it, which I have it, it's defined in ceval, and you have two defines. This is the py begin allow threads. You open this, say, okay, save, py thread state, a variable save equals py eval save thread. So you're starting this. And fun fact is it doesn't have the closing bracket. It's defined only here. So you start with this, you finish with this, and let other threads run. You should be polite and hand over this GIL to other processes, tell processes when you need it, when you don't need it, and all of this stuff, which makes things a little bit more difficult. That's py eval release lock and acquire lock should be in Python. It was part of the states. Maybe QRS. We don't have states. Py states, I believe. No. Yes, py states. These are the functions. We have to control this GIL states. It says, for example, when a thread state is created for a thread by some mechanism other than blah blah. This is the ensure we are using. It's important that the GIL state mechanism knows about it. So we have this T state. What we had, release lock, for example. We have the release lock. This is the, for example, release. If not holds GIL in this T state, do this, for example. If you want to release but you don't have it. Anyway, I don't want to waste your time and read the code for myself. I haven't read them previously and don't know much about them, but it can be a very fun read. Now you have a good understanding of what is GIL, why GIL is problematic, and we can speak about some other solutions. In different times, people try to remove GIL for many times. For example, in 1999, there was a project which was very famous then, and Python was new. It was free threading, and threading even was new for me, at least. Later, in 2015, we have a very cool name, Gilectomy, if I'm right. And it was trying to, like vasectomy or lobotomy, remove the GIL from the Cpython. But none of these went to the production release of Cpython. But now we have a project which is called nogil. This is introduced by Colesbury, Sam Gross. Huge work with a team for sure. I don't believe that he's alone. If he's alone, I respect you even more. On 2022, I think, in PyCon, he said what he's doing, introduces this. Many people tried this, very impressive results. Also, he and sponsor Mr. Langa, your peps should have a sponsor so people won't just submit peps. With the sponsorship of Langa, who's a core developer, and Sam Gross proposed this, that we can start removing the GIL. And now it seems the steering committee on the Python is okay with it, and they have started removing the GIL step by step. You saw how many GIL references we had, and it's very, very difficult task. Kudos to Mr. Gross to doing this very, very, very impressive work. And there are some issues for sure. There are people who used this nogil and did benchmarking on different programs. You saw how easy GIL is. You have different threads. You just run the thread which has the GIL. It runs the bytecode, Python bytecode. Removing the GIL makes things a little bit more complicated, because you should know which variable is being used where, if you are has conflicts on them, if two different things are trying to write to the same object, memory management and everything. It will make things more difficult. If you read this PEP, I haven't read thoughtfully all of it. This is what I was waiting for, but I will read. But they will describe how they are implementing changes. They are grouping them in 4 different categories: reference counting, memory management, container thread safety, and locking and atomic APIs. So they need a huge revision on the Cpython code. It needs more work, and even Cpython needs more work. And the one huge problem is Cpython will be slower because it should do more things. If you have a program with lots of threads, some people say it makes 15 to 30% faster. Your program will run faster on the new nogil Cpython because GIL is not there anymore. Concurrency is better. 2 different threads can run non-overlapping bytes code, and this makes everything much more faster and is impressive. But if you only have one thread, GIL was very easy. Your thread was asking for GIL and just running and running and running. But now Cpython needs to do more checks on what a thread does, how it's accessing variables and everything. And in some people say it makes up to or more than 10% slower what was working on only one thread. This is why people are kind of not super happy with this. And how many programs do we have? What was the last time you wrote a program or seen a program running on threads? Just in this video, I wrote one for you, but that was experimental. But okay, maybe more than 60%, just a guess, of our programs are just normal Python programs on one thread. We are not importing threading or multiprocessor or whatever. So, parallelism, I mean. So, those programs will run a little bit faster. Meanwhile, everyone is asking for faster Python. There is a project, I cannot remember if it's faster Cpython or fast Cpython. And they're trying to make Cpython faster. Nobody wants to say C next release and all our normal non-threaded programs will be run not much, but somehow observable slower. And when we say why, it's okay, but we got rid of GIL. And people will come to you and ask you, what is this GIL? And you have seen this video, so describe to them why it's important. But many of the important programs in our company, everything is running on threads. So more professional people will be happy, data scientists will be happy, people who has CPU bound and highly CPU intensive programs will be happy. And these are different ideas. If you want to know more, there are some good articles. Real Python has one. What is the Python global interpreter like? Another a little bit more history and in-depth is the Python GIL, past, present, and future from Backblaze. You can find. I will add this to the show notes. Another very good one is GIL Removal and the faster Cpython project from LWN. This one will try to describe how this parallelism work, how you can run concurrent even when you are getting rid of the GIL, how it should work and everything. This is more into the real history with real email comments and everything. We don't want to repeat Python 2 to Python 3 transition. We don't want to break backward compatibility and lots of stuff. And Python glossary, PEP 703 is the one which is describing this. And if you had time, it's a good experiment to try to compile nogil. Try your programs in this, see if it's faster, if it's slower. And I hope you enjoyed this kind of long but interesting video. Interesting in my point of view, otherwise I wouldn't record it. Thank you. I would be glad if you subscribe, tell your friends, will give me more hope, no, more joy, no, more, may improve my English.